Inside the shadow of Geneva, under the world's floor, lies a shock of human imagination and a typical harbinger of pulverization. The huge Hadron Collider, LHC. It is a manual of savvy assessment, allowing experts to look at the subatomic at large and affecting the divulgence of the perplexing God molecule, the Higgs boson. At this point, prominent physicist Brian Cox has made a chilling announcement that sent shockwaves all through the strict community. Something critical has been investigated at CERN, something that may have achieved extended ways past our perception. Has our fundamental objective of illuminating informative combinations set us on a compressed lesson, with disaster obliging us as we dive into the pit of this unmistakable issue? Yet, sooner than we jump into the declaration information, what sizable atom smasher pedals the massive LHC? Operated by CERN, it is a 17-meter ring of superconducting magnets and the field's most significant and strongest particle collider. It represents the peak of human scientific accomplishment. The reality of the situation is so strong that it can repeat the certified states of the universe's creation. Should this development expect to open the insider estimates of the universe, it remains aware of the way to something plainly more significant, potentially problematic. CERN, founded in 1954, is one of the world's most critical scientific research organizations, with 23 member states and a huge range of experts. It is a focal hub for joint efforts and advancements. The LHC is CERN's central endeavor, but it's only one part of a tremendous organization of gas pedals and detectors. This includes the LHC, which is designed for subatomic particles and is dedicated to the study of existence itself. The LHC speeds up protons to almost the speed of light, sending them on a crash course that mirrors the energy of the universe at the time of the Big Bang. The impacts create temperatures 1 million times hotter than the center of the sun. An epic cluster of magnets directs the protons on their way, while cutting-edge cooling systems maintain the magnets at temperatures colder than space. These include 1,232 dipole magnets that steer the beams and 92 quadrupole magnets that center the beams before impact. Another type of magnet is used to pack the particles together to improve the probability of crashes. The task of CERN is to impact particles with such precision that they meet exactly. The accuracy required is bewildering. The LHC's design is a wonder of engineering, with parts pressed very close together, arranged with accuracy estimated to within 574 feet. The entire system is cooled to a temperature of 46 degrees Fahrenheit, colder than the vacuum of space itself. This cool climate is essential for the superconducting magnets to work ideally. The LHC's detectors are situated at 4 locations around the accelerator ring, corresponding to the areas of 4 significant particle experiments: ATLAS, CMS, LHCb, and ALICE. Each plays a specific role in examining special parts of particle physics. In general, these detectors capture massive amounts of data from particle impacts. Experts then filter through this information for proof of the subtle Higgs boson, otherwise known as the God molecule, an interesting inconsistency that holds hints to the universe's basic structure. It's likened to chipping away at an eternal jigsaw puzzle, where the pieces are invisible and the image is challenging to recognize. By zeroing in on the microcosm, we gain bits of information about the universe, but with each disclosure comes new inquiries and challenges. The LHC isn't just a surprising scientific instrument. It is a symbol of human curiosity, progress, and the journey to grasp the principal powers of the universe. However, as we stretch the limits of our insight, we must also consider the moral and existential questions that arise. What are the risks of testing the unexplored world? Should our journey for greatness startlingly release powers we can't control? Inside the hallowed halls of CERN, where the wildernesses of human understanding are constantly pushed, an ongoing disclosure has sent shudders down the spines of even the most prepared researchers. Brian Cox, a former CERN scientist and a prominent voice in particle physics, has made a statement that has left mainstream researchers both enamored and frightened. Cox's comments reflect an overwhelming possibility. The LHC will likely reproduce a scaled-down Big Bang, an event that first formed our universe. The physicist also discussed the potential ramifications of this goal, highlighting the LHC's ability to reveal new elements of understanding, including insights into dark matter, a substance that is a critical part of the universe. considering the possibility of witnessing the real essence of the universe is an appealing opportunity, but one laden with risk. Reproducing a Big Bang isn't simply theoretical. It involves real conditions that repeat the universe's early stages. With such power comes real responsibility and the need for careful consideration of potential dangers. Consider the situation where something goes wrong. In 1978, Russian physicist Anatoly Boryk encountered an accident that might have changed his life while working at a high-energy physics lab in Russia. A proton beam accidentally passed through his skull, entering through the back of his head and exiting through his nose. Despite this devastating event, Boryk survived and continued his work, although he experienced some severe medical problems. This occurrence isn't just a story. It's a wake-up call, illustrating the enormous energy and potential dangers associated with particle accelerators. The risks of particle accelerators like the LHC are not to be taken lightly. The potential for unprecedented reactions and the control of fundamental insights requires careful safety protocols. Among the most disturbing possible outcomes is the production of miniature black holes, regions of space where gravity is so intense that not even light can escape. These hypothetical substances could have unanticipated consequences if they were to grow uncontrollably. Despite extensive safety measures, the chance of creating a black hole or other extreme anomalies cannot be completely ruled out. Theoretical models suggest that any black holes produced would dissipate rapidly, posing no threat to Earth or its occupants. Nonetheless, the very idea of potentially generating powers beyond our control remains unsettling. As researchers push the limits of our understanding with the LHC, it is essential to do so with a careful awareness of the associated risks and uncertainties. The quest for knowledge involves exploring these possible risks with transparency and public engagement. The Large Hadron Collider, with its remarkable capabilities and potential for groundbreaking discoveries, stands as a testament to human creativity and the tireless pursuit of understanding. However, beneath its grand exterior lies a domain of significant scientific inquiry, filled with potential dangers and ethical considerations. The tests conducted inside the collider involve energies and forces beyond the comprehension of most people. The effect of subatomic particles at near-light speeds recreates conditions present in the universe's earliest moments, allowing scientists to explore fundamental components of matter and the actual fabric of space-time. While these investigations offer tremendous potential for discovery, they also carry substantial risks, both known and unknown. In summary, as we continue to explore the mysteries of the universe through the LHC, it is essential to balance our pursuit of knowledge with a deep awareness of the potential consequences and a commitment to rigorous safety practices. CERN is a leading research center for particle physics. Its flagship project is the Large Hadron Collider, LHC, the world's most powerful particle smasher. The LHC smashes protons and other particles together at near-light speeds, allowing scientists to probe the fundamental components of matter. Unforeseen discoveries in particle physics could involve new particles or phenomena, finding particles that were not predicted by the standard model of particle physics, for example, or anomalies in the data could suggest new particles or unexpected behavior of known particles. Observations that don't align with existing theories could indicate new physics beyond the standard model, such as supersymmetry or dark matter. Brian Cox, known for his ability to explain complex scientific concepts in an engaging way, would contextualize the discoveries, explaining what these new findings mean in the broader context of physics. How do these discoveries fit into our current understanding of the universe? He could also discuss the implications and how these findings could impact future research. This could include changes to theoretical models or the design of future experiments, as well as communicating these discoveries to the general public through clear, captivating language. The Higgs boson, discovered in 2012, was a key part of the standard model. Its discovery confirmed the existence of the Higgs field, which gives particles mass. The discovery of antimatter and the behavior of particles like positrons, the antimatter counterparts to electrons, has led to huge advances in understanding the symmetry of the universe. Observations of neutrino oscillations provided evidence that neutrinos have mass, which was not included in the original standard model. Surprising discoveries often lead to new theoretical models. These could propose new particles or forces that could explain the observed anomalies. Further experiments might be designed to explore these discoveries in more depth, possibly at different facilities or with new technology. Cross-disciplinary insights could emerge, affecting fields like cosmology, material science, or even technological advancements. Brian Cox plays an important role in interpreting these complex discoveries for the public. Through media appearances and public talks, Cox regularly shares exciting scientific developments, ensuring that the general population stays informed about cutting-edge research. He could produce educational content like documentaries, online talks, or books to help audiences understand the significance and potential impact of these discoveries on our understanding of the universe. Unexpected discoveries at CERN can have far-reaching influences. Technological advancements developed for high-energy physics often lead to progress in other fields. For instance, the World Wide Web was originally created at CERN to facilitate collaboration among physicists. Philosophical and conceptual shifts can also occur, such as discovering evidence for a multiverse or fundamentally new structures of matter, which could profoundly affect our understanding of existence and reality. Looking forward, CERN is planning upgrades and new projects that could lead to further unforeseen discoveries. High-luminosity LHC upgrades are focused on increasing its brightness, allowing more collisions and more data, which could lead to the discovery of intriguing phenomena. Future colliders, like the proposed Future Circular Collider, FCC, are being developed. These new facilities could investigate even higher energies and more fundamental questions. Advances in quantum computing and data analysis could revolutionize the study of the vast amounts of data produced by experiments at CERN.